CH572
Hi everyone, I'm going to go ahead and get started. We begin by sharing my screen. Okay, still admitting a few more people here. Okay. Okay, we're going to continue looking at reactions of alcohols. Okay, this is the overview. Okay, we looked at dehydration in terms of when we talked about E1 eliminations. Okay, last time I introduced oxidation. Primary alcohols are oxidized either to aldehydes or carboxylic acids. Secondary alcohols are oxidized to ketones, and tertiary alcohols are not easily oxidized. Okay, some of the ways of oxidizing alcohols include chromium reagents like sodium dichromate and sulfuric acid. The active agent is probably chromic acid, H2CrO4. There is a color change that accompanies this reaction from orange to blue-green as the chromium gets reduced. Right, this is one that we've done in lab, not our class, but in previous years, we've done this one in lab, where we use bleach and acetic acid. Okay, this produces environmentally benign byproducts, acetic acid and sodium chloride. Okay, this is the mechanism for formation of the chromate ion. Then the chromate ion forms chromate esters with alcohols. Okay, it's right here, this step. This explains why tertiary alcohols are not easily oxidized. They lack a hydrogen at this position. Okay, and that goes not just for dichromate, but for other oxidations. It is, I'm going to move through this fairly quickly. So this is review. Primary alcohols with dichromate go all the way to carboxylic acids. PCC and some other methods like the Swern oxidation and the DMP allow us to stop at the aldehyde. Okay, all of these methods will take secondary alcohols to ketones. The liver oxidizes alcohols using alcohol dehydrogenase, which acts as a catalyst, but the oxidizing agent itself is NAD+. Ethanol is oxidized to acetic acid, which is a normal metabolite. Okay. Alcohols can act as nucleophiles. Sorry. Okay, for example, they can attack carbocations to form new covalent bonds. Alcohols themselves are weak nucleophiles. If we make the alkoxide salt, then that's a strong nucleophile. And alkoxide salts are typically made either using sodium or potassium metal. Okay, this produces RO minus, which is a strong nucleophile. The substrate has to be primary or methyl. Okay, otherwise you get E2 elimination. Getting back to the last bullet point, the hydroxyl group is a poor leaving group. What we did in 2 of our labs was that we protonated the oxygen so that water was the leaving group. Actually, we did that in 3 of our labs if we count the dehydration of cyclohexanol. Okay, this is a reaction that converts a poor leaving group into a good leaving group. Okay, we make a tosylate or toluene sulfonate ester. Okay, water is split out and we form this ester. We reconnect the oxygen with this sulfur. The actual reagent that's used is tosyl chloride, okay, where we have a chlorine here instead of an OH, and then pyridine to neutralize the HCl that's produced. The tosylate group is an excellent leaving group. We can use it for both substitution, usually SN2, and elimination reactions, usually E2. Okay, so here's an example of an SN2. The tosylate ion is a good leaving group because it is a weak base. It's very stable because of all this resonance delocalization of the negative charge. Okay, we can do many reactions on a tosylate group. Okay, for example, we can go back to the alcohol. If the alcohol were on a chiral center, this would give us inversion of configuration. Okay, in fact, all of these would give us inversion of configuration. Okay, we can make amine salts, ethers, alkyl halides, nitriles, and we can also use lithium aluminum hydride to make alkanes. 2 ways to reduce alcohols. We can dehydrate to the alkene and then hydrogenate, or we could use lithium aluminum hydride after we've made the tosylate. We can convert alcohols to alkyl halides using HCl, HBr, HI. This is not always the best way to make that conversion. It does produce a better leaving group. And as we saw in the case of the SN2, it took a long time. It was a slow reaction to convert N-butyl alcohol to 1-bromobutane. Okay, we can readily convert tertiary alcohols to tertiary halides, as long as we control the temperature by an SN1 mechanism. Okay, I'm going to review the Lucas test. That's a mixture of zinc chloride and HCl. Okay, and the idea here is that primary alcohols react either very slowly or not at all. Secondary alcohols within 5 minutes and tertiary alcohols within 1 minute. Okay, this converts the alcohol to the alkyl halide, and what you see is either a precipitate or a white cloudiness. Okay, so here's the SN2 reaction, which we said was very slow, even though this is a very good leaving group. Okay, some of the limitations of using HCl, HBr, and HI: get poor yields of alkyl chlorides from primary and secondary alcohols. We can get elimination, we can get carbocation rearrangement. Okay, these are some examples of rearrangement. We can overcome some of these limitations by using phosphorus halides. Okay, PCl, PBr, PCl3, PBr3, or PI3, which is typically made in situ using elemental phosphorus and elemental iodine. Okay, to make neopentyl bromide using HBr would not give you good results. Okay, it's a primary alcohol, it's hindered. We'd get rearrangements if it reacted at all. But with PBr3, okay, this works fairly well. Okay, we have some other, here's a primary, here's a secondary halide. We can make the corresponding, primary, secondary alcohols, we can make the corresponding halide. And here's the mechanism. Alcohol attacks phosphorus, kicks out a bromide. Bromide then comes around to the backside and displaces this leaving group. Okay, this is an excellent leaving group, so this occurs very readily. And because Br minus attacks from the backside, we would get inversion of configuration if it were on a chiral, if the leaving group were on a chiral center. Okay, the stoichiometry is 3 alcohols to 1 PBr3. Okay, thionyl chloride also works well to convert alcohols to alkyl chlorides. Okay, byproducts, as I mentioned, were gases that can easily be removed. Okay, went through the mechanism. Okay, I'll go through it quickly again. Alcohol attacks sulfur, pushes a pair of electrons up onto the oxygen. Chloride gets kicked out. Chloride removes the hydrogen. Okay, so we get HCl. We get a alkyl migration that takes place. And chloride then dissociates and attacks the carbocation. Okay, we've already talked at length about dehydration. This is the exact same reaction that we did in the lab. We will talk in a little bit about the second to the last bullet point here and the third to the last, bimolecular dehydration and ether formation. In addition to sulfuric or phosphoric acid, another way to carry out a dehydration is with phosphorus oxychloride, POCl3, and pyridine. Okay, this takes place under milder conditions than phosphoric or sulfuric. HCl is not typically used for dehydration since concentrated HCl is about 62% water. Okay, you can get rearrangement since it is an E1. The rate of formation depends on the substrate. So tertiary is fastest, followed by secondary, followed by primary. Primary alcohols do rearrange, so this is not a good reaction for converting primary alcohols to alkenes. Okay, here is bimolecular condensation to form ethers. Okay, when we convert ethanol to ethylene, that takes place industrially at 180 degrees Celsius. This reaction takes place at 140 degrees. Okay, when ethanol gets protonated, a non-protonated ethanol can attack, kick out water. Another ethanol comes along, removes this extra proton, and we get ethyl ether. Okay, industrially, this is how ethyl ether is made. Okay, this is called a condensation because we split out water ultimately. Okay, this reaction does not work if we're trying to make an unsymmetric ether. Say we wanted to make ethyl propyl ether. Okay, we would get all possible combinations. We would get diethyl ether, dipropyl ether, we would get propyl ethyl ether. Right, there are some unique reactions of diols. Vicinal diols or glycols can undergo two reactions, two notable reactions, the pinacol rearrangement and periodic acid cleavage. Okay, this is the pinacol rearrangement. It takes place in sulfuric acid at 100 degrees. This is commonly called pinacol. It's 2,3-dimethyl butane 2,3-diol. And this is what we get. We get a ketone, okay, which is commonly called pinacolone. Okay, so in the pinacol rearrangement, a vicinal diol converts to the ketone under acidic conditions and heat. Okay, it is classified as a dehydration, even though we don't get an alkene, but we do lose water in the process. Okay, so here's the mechanism. Okay, as we would expect, oxygen picks up a proton from sulfuric acid. Then water leaves. Okay, just one of these gets protonated. Water leaves. And okay, we've got a tertiary carbocation. And as a tertiary carbocation, you probably wouldn't think that would rearrange, but it does. So we get a methyl shift. And it turns out that this resonance stabilized cation is more stable than the original tertiary carbocation. Okay, so we can delocalize the plus charge on the carbon and on the oxygen. Okay, so in the last step, if we look at this resonance form right here, water comes back, removes that proton, and then we get this ketone. Okay, next we'll look at periodic cleavage of glycols. Okay, we can make glycols, especially cis glycols, using OSO4 and hydrogen peroxide. And then we can cleave them using HiO4. This is periodic acid. Okay, that cleaves, that actually breaks this carbon-carbon bond and gives you a combination of aldehydes and ketones depending on what these other bonds were to. Okay, historically, this has been used to determine the structure of sugars. It can also be used for ring opening, for example. Make that a little bit bigger. Okay, this is a periodic table. All right, here's the mechanism of HiO4 cleavage. Okay, we actually get an intermediate, which looks a lot like the intermediate in the OSO4 reaction and in the cold dilute permanganate reaction. Okay, so we have a cis glycol. That turns out that's important. These groups have to be cis. And we form this cyclic periodate ester, and it undergoes cleavage to, in this case, a ketoaldehyde. Okay, since we have an H here, this side becomes an aldehyde, this side becomes a ketone. Okay, next we'll look at esterification. Okay, we've already seen one type of ester, and that's the tosylate. An ester involves the condensation of some kind of an acid and an alcohol with water being split out. But we can also have esters with sulfates, with nitrates, with phosphates, for example. Right, in Fischer esterification, we take an alcohol and a carboxylic acid, and using a little bit of acid catalyst, usually a small amount of concentrated sulfuric acid. Okay, water gets split out, we get our ester, and water is a byproduct. This reaction is in equilibrium, it's reversible, and so we would not get good yields if we used the same molar quantities of alcohol and acid. Okay, even though the reaction says it's a 1-to-1, but it is reversible. Okay, so this will go until equilibrium is reached. So the reaction will go backwards to starting material. And one way to shift it toward products would be to use an excess of either alcohol or carboxylic acid. Okay, and this also typically takes a long time to reach equilibrium. Okay, sometimes even several hours to reach equilibrium. Okay, this is generally a better way of making esters than the Fischer esterification, and that is to use an acid chloride. There is a base added, very commonly, pyridine is used. Pyridine is both a solvent and it acts as a base. Okay, we're producing HCl as a byproduct, and so pyridine will neutralize the HCl, and that prevents the reaction from reversing. Okay, we can use other bases as well. Another one is triethylamine, a nitrogen with 3 ethyl groups on it. That would also work. Okay, this reaction is exothermic. It produces the corresponding ester in high yields. HCl is the only byproduct, and then pyridine neutralizes the HCl. So we could actually use theoretical or stoichiometric quantities of alcohol and acid chloride. We don't have to use an excess. And this reaction goes rapidly under milder conditions than Fischer esterification. Okay, here we have nitrate esters. This is glycerol, 1,2,3 propane triol. And if we treat it with a mixture of nitric and sulfuric acids, we form nitrate esters. Okay, this is glyceryl trinitrate, otherwise known as nitroglycerin. Right, nitroglycerin is very unstable. It is explosive. It was too unstable to use in mining, and so Alfred Nobel, for whom the Nobel Prize is named, discovered that by mixing it with diatomaceous earth, he could stabilize the nitroglycerin, and that resulted in dynamite. So he was the inventor of dynamite. Okay, one irony of the story was that Alfred Nobel was having heart problems, and it was recently discovered that nitroglycerin could be used to treat heart attacks. And while he was having a heart attack, he refused to take nitroglycerin. He couldn't believe that something so explosive could have a therapeutic value, and so as a result, he did die of the heart attack. Okay, there is a number of other nitrate esters that are used. Most of them are explosive. There's one that's called PETN. Drop here. This is one called PETN. Okay, and then if you take cotton is cellulose. It's a polymer of glucose. It has lots of OH groups. And if you nitrate some of those OH groups, you get something called nitrocellulose or gun cotton. I'm going to show you a video of nitrocellulose. I'm going to stop sharing for just a moment while I locate that. I've got one here. Okay, so I'm going to share my screen here again.
Yeah, I think people why would seriously eat people.
Okay. Here, some more gun cotton. Looks like his candle keeps going out. Yeah, there you go. Okay. All right. Okay, let me hang on just a minute. Let me try to. Shut off YouTube here. Just a minute here. And okay, shut that off. Okay, go back to the PowerPoint. Oops, wrong one. Sorry about that. Here we go. Okay. So phosphate esters are very important not only in organic synthesis, but also in biochemistry. Okay, here's phosphoric acid. We can esterify 1, 2, or all 3 of these OH groups. Okay, so here is dimethyl phosphate. Here's trimethyl phosphate, monomethyl phosphate. Okay, in DNA, we have what's called a phosphodiester linkage. the structure of DNA consists of three main parts. There's the base, there's the deoxyribose sugar, and then there's the phosphate group. Okay, each deoxyribose is connected to a base, and each deoxyribose is connected to another deoxyribose by this phosphodiester linkage. Okay, here we have synthesis of ethers using alkoxide ions. Okay, this is something that we've actually seen before. If we take an alkoxide ion and we react it with a primary or methyl halide or tosylate, we can make an ether. Okay, this substrate has to be primary or methyl. This one could actually be anything. It could be phenyl, it could be primary, secondary, tertiary. Okay, and again, if we use anything other than a primary, we'll get elimination. Primary or methyl will get elimination. Okay, so that is all for chapter 11. And I'm going to go ahead and stop there a few minutes early. Okay, there's no class on Wednesday. And then we'll have another remote session on Friday.